Good afternoon, everyone. Dr. Daniel Barth here with the How Do You Know program. And this week, we're going to be talking about some mysterious new objects unlike any science has found before. But let's take a look at astronomy and space science news today. This is kind of space exploration news. Scientists at the University of Surrey over in England have developed a new paint that they call living paint. What they've done is they've embedded cyanobacteria, blue-green algae bacteria basically, which is an extremophile species. Cyanobacteria can grow in extremely hot environments, cold environments. It can withstand near vacuum, lots of radiation. It's tougher than cockroaches. It's amazing. One of those very, very durable species of life. They've embedded this stuff in paint, my friends, and the idea is that this bacteria in the paint not only produces oxygen, but it captures CO2. And they are making claims that the paint can produce 0.4 grams of oxygen per gram of biomass. So you figure for every gram of bacteria material they add into the paint, they get about 0.4 of a gram of oxygen per day, and it captures as much as 0.3 grams of CO2. Now that doesn't seem like it's very much, but a gram of bacteria is a very small amount. And I'm imagining a gram of bacteria wouldn't cover an area more than a few square inches. So if you're talking about painting the interior of a space habitat or a lunar habitat or a Martian colony habitat with this stuff, not only would it produce oxygen for the astronauts and scientists and engineers living there, but it would capture CO2. And these are two of the primary requirements. And if any of you remember the movie Apollo 13, what was one of the big problems there? They went ahead and they were having problems capturing their CO2. So this is a big bit of news and holds great promise for future space exploration. And let's take a minute and talk about your next book purchase. I know everyone here is interested in astronomy, and this is the time of year. I know you get the questions that I get. Hey, Doc, I want to buy a telescope for my husband, wife, child, friend, and what should I get, and what other things do I need? And when you think about getting someone started in the hobby of astronomy, you want that to be a lifelong pursuit. You don't want them to buy something and go, oh yeah, I tried it for a while, I don't like it anymore. I wrote the book Star Mentor just for you, just for your friends, your spouse, your children, someone who's getting started in astronomy. And for those of us who have been in astronomy for a while, where people come and tug on your sleeve, oh, can you teach me this? Can you teach me that? Recommend the book to them because it's a great hands-on resource. And if you're involved in outreach, it gives you lots of things to do, and it describes how to teach, how to explain to a newcomer, how to get them to learn how to operate their telescope, read a star map, and learn a bit more about what they're observing. Here at Explore Scientific, we all recommend Star Mentor, and lots of our customers swear by it. Now, let's go ahead and take a look at other news that's come up. What would you say if I found a way that I could darken your skies by 90%? Take it from a Bortle 2 or 3 where it's gray and kind of hazy and you can see only the brightest stars to something that was substantially darker. Well, scientists, this gentleman is called, I'm hoping I'm getting his name right, Vlad Pashkovsky. Mr. Pashkovsky has founded a company called Stealth Transit. And what he's doing is he's working on a way of changing your LED lighting. LED lighting has become a big thing in cities, roadways, outdoor lighting. Why? It's energy efficient, but we're also finding that it's a lot brighter than the standard incandescent type fixtures that they're replacing. As a result, light pollution is becoming a great big problem. And Mr. Pashkovsky's idea is to wire all the LEDs so they blink on and off 150 times a second. If you know anything about movies or TV broadcasting, after about 24 frames per second, the human eye really has trouble distinguishing individual frames, becomes like a smooth motion, and at 150 frames per second, that's like a TV going at 150 hertz, it really is too fast for the eye to detect it all. However, Stealth Transit's idea is that now we take your telescope, and between your telescope and your camera, we're going to put a digital shutter that's going to basically blink the camera's sensor on and off 150 times a second, and the sensor will only gather light during that very brief period in between blinks when all of the LEDs around you in the city and across the country are off. So if you've ever experienced a blackout, if you're like me, power loss is like, oh boy, if it's clear skies, let's get the telescope out, because all the street lights and all the local area lights are out and your skies are suddenly marvelous. Stealth technology, self-transit rather, promises this 90% reduction in light pollution for people using photographic techniques. This would, of course, include all the professional observatories, and it could be made inexpensive enough, we hope, for amateur astronomers with their cameras and their sensors to take advantage of it. No word on some sort of an optical shutter. I know cameras with mechanical shutters can go ahead and expose and open and close a shutter that quickly, but whether or not you could get a shutter system that would go at 150 hertz continuously for optical purposes, I'm not sure. Let me ask our producer, Paul. He's a lot more familiar with camera technology than I am. Paul, do you know of a camera that could go 150 frames per second over an extended period of time? Do they have that technology?
Yeah, absolutely.
Wow. I want one for my telescope. I really do. This is so exciting to me. And we'll look forward. This is not a product on the market yet, friends, but we'll look forward to it. And we hope to, if I hear more news from Stealth Transit, we'll definitely share it with you here. Also want to share with you that Explore Scientific now has a CPO, or Certified Pre-Owned program. I know for a fact that we've been packaging up binoculars and telescopes of all sizes. I saw back today, behind the scenes here, that 10-inch Dobsonian, what is a glory telescope, a lifetime telescope dream for many astronomers. We're going to be having some in certified pre-owned quality. And these CPO products, friends, you may see slight mars on the finish, things like that, but optically perfect. Nothing that would interfere with your enjoyment at the eyepiece of either telescopes, binoculars, eyepieces, etc. So if you're shopping for a bargain this year, or if you're looking at purchasing a new pair of binoculars or telescopes, you might want to give Explore Scientific a call and ask them. Keep in mind that CPO stuff is very limited stock, and it's here today, gone tomorrow, and the inventory varies a lot. So it's not like regular telescopes and binoculars where Explore has them in stock all the time. The inventory on certified pre-owned products vary, and we encourage you to keep in touch with the good folks at Explore and talk to our customer service reps. They will have the information for you.
So
now,
Dr. Barth,
sir,
John Ray says, Hello, Dr. Barth from Cornish Flat, New Hampshire. I'm really looking forward to this week's How Do You Know. I received my copy of Star Mentor, and I have donated it to our local library who participates in loaning telescopes.
That's so exciting. And John, we heard from you in previous weeks. I'm glad you got your copy. I hope you had a chance to look it over and enjoy it for yourself a little bit before you donated it, but that's great. And I hope you'll leave a review on Amazon for us, because for me as an author, speaking as an author, reviews are not only very important feedback for me, but they help other people find the book and find this resource. This book, John, was more than 40 years in the making. When I first started teaching astronomy back in the mid-1980s, my dean didn't believe I could do it. No, I don't want you to do that. An astronomy course, what could you be thinking? And so I said, let me have an astronomy club. If it goes well for a year, let me have a class. They said okay to that. It was very popular, obviously. And they said, but how will you do it? There's no textbook. I was teaching high school at the time. And I said, it's okay, I'll write one. I got a lot of hee-hee, titters behind the hand, eye rolls when I said that. But no, I did write a book, Observational Astronomy, which I used for teaching astronomy for many years. And what I did is I took 40 years of astronomy teaching experience, and I sorted through all the lessons, all the activities, all the laboratory exercises that I had created, virtually all of them from scratch, because when I started teaching, there weren't any resources and there wasn't any internet. So I had to create all this on my own. And I took the best of this, some 50 activities with lots of follow-up, and put it into Star Mentor. And I've mentioned before, there's a lot of illustrations and drawings. All the drawings are mine, for better or for worse, but I hope you'll all enjoy them. And John, I hope I'll look forward to looking for a review from you soon. Let's go ahead with today's topic. And these are Jupiter mass binary objects. And of course, astronomers love acronyms. I'd love to be in on the party where they're inventing these things. They're calling these jumbos, J-U, Jupiter mass binary objects, jumbos. And I want to kind of take you through this, because if you're an astronomy and space science geek, as I am, just reading this headline was very exciting, but I know a lot of people need a bit more background and a bit more so you know how we know. How do you know about Jupiter mass binary objects? We started off, and these were detected in ground-based observatories. Now, the problem, of course, we're looking inside the Orion Nebula, M42, and we're getting into that time of year where if you're up late enough, you can see M42, and in midwinter and early spring, Orion is a glorious object, everybody's winter favorite. And we've known for a long time that Orion is a star-forming region of places where clouds of gas and dust are condensing through gravitation, and these clouds of gas become locally compacted. Compression creates heat, and eventually the cores become hot enough at about 10 million degrees centigrade. Well, 10 million centigrade Kelvin is it's very much the same thing. And at that temperature, we start to get hydrogen fusing into helium. And once the fusion reaction kicks off, you have a true star. Before that, where it's just a hot compressed ball of gas and dust, it's referred to as a protostar. And we've known that Orion has been a star-forming region for a long time, and that it has a lot of mass there, thousands of solar masses of gas and dust. So it has been a star-forming region for millions of years, and it shall be for millions of years to come. The problem is, looking into a dusty region is hard. Dust absorbs light in the visible wavelengths. The redder the light is, the easier time it has penetrating through the dust, but if you know your spectrum, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, everything in frequency above red gets filtered out by dust. That's why we have, especially in the Midwest where I'm located, in the fall, when it's time for the farmers to bring in the hay and bring in the crops. And this does throw a substantial quantity of dust in the air. In the spring, when the trees are giving off a lot of pollen, much the same thing, these act as dust particles. And we get these spectacular red sunsets and that are absolutely glorious. And if you've watched one of these sunrises or sunsets, as the sun rises higher, the sunlight is traveling through less air. Remember, our atmosphere curves around the planet, so if you're here and the sunlight is coming just at sunrise or sunset, it's traveling through many hundreds, almost 1,000 kilometers of air, where straight up and down at noon, 60 to 80 kilometers of air. And so dust in the atmosphere filters out all these other colors of light. Same principle holds in the Orion Nebula. Much of the visible light is absorbed, and so with a ground-based telescope, it's hard to penetrate into that nebula visually. The other problem, of course, is that Earth's atmosphere is full of water vapor, and water is an extremely efficient absorber of red and infrared light. You might know this if you've ever filled a pool in your backyard that you want heated by sunlight. It takes a long time for just the sun to heat that pool because water has a great capacity to absorb heat and so a great capacity to absorb and block infrared radiation. This is why when we made this huge infrared observatory, the James Webb Space Telescope, we put it out in space well away from Earth's atmosphere and interfering light, and it's able to see in infrared and with infrared light penetrate into the interior really better than any telescope system before in history. And so when ground-based observatories at the threshold of their ability to detect said, we think we're seeing Jupiter mass things. They might be brown dwarfs, they might be planets, we don't know. We're seeing these indications, but the dust makes it hard for us. And so we trained the James Webb Space Telescope on Orion. I'm sure all the astronomers who were controlling and the principal investigators were just cackling with glee because Orion has been a favorite of everyone for a long, long time. Now, the fellow who's in charge of this investigation is Professor Mark McCaurin. And Professor, I dearly hope I'm saying your name correctly. And he is senior advisor to the European Space Agency for Science and Exploration. So he's one of their most senior scientists and astronomers. And to quote him, he says, "We were looking for very small objects, and we find them." This had to be a very, lots of hand claps and high fives at that time when that data came down. He said, we find these down to as small as 1 Jupiter mass. Some of them are even as small as half a Jupiter mass, which puts them in the class of a planet like Saturn. Now, these are freely floating and they're not attached to any star. You may know that there was a telescopic survey some time ago, and it was looking for changes in brightness. It was looking essentially for eclipse events. Can we see stars that are being eclipsed by planets passing in front of them? And they found out that, when we look at this, oftentimes we can see that the star and the planet are gravitationally interacting. But these folks doing this survey found, there are lots and lots of planets out there that seem to be drifting in front of stars. They had a lot of detection events. And they ran the math and they said, this comes out to a number of perhaps 10 to 100 trillion rogue planets freely drifting through interstellar space in the Milky Way. And if you think about that, that vastly outnumbers the number of stars in the Milky Way. And yes, more planets than stars. This makes sense intellectually. And we just don't think about this early formative period of star systems where planets are forming sometimes in close or similar orbits, and they gravitationally interact. And as we found out last time, sometimes they collide. Bam! But when they don't collide, sometimes there's a miss and they play gravitational crack the whip, and planets can actually, big planets, can be ejected from solar systems to become rogue planets. Now, I will say that Professor Makarian, he shies away from the term planet. The whole controversy of, is it a planet or isn't it? I used to harass my astronomy students back in the day and assign for them, okay, your only assignment for the day is bring back a definition of the word planet and tell me where you found it. And the dictionary doesn't count. You have to find it in a science book. But it wasn't there. Astronomy is a very ancient science. Humanity has been doing astronomy for 10, 20, 30,000 years. We have carbon-dated moon maps that date back 20,000 years. And so the idea of planet is very ancient, and as our understanding of the universe grows and improves, our idea of planet has changed. I'm going to help Professor Makarian here. Yes, these are planets, Professor. And I don't make these claims without citing evidence. That's not how we know. But there's something in astronomy known as the Vogt-Russell theorem. And Herr Vogt was a German scientist, and he came up with this idea first. And Russell is he of the Hertzsprung-Russell diagram fame. And both of these scientists, and Vogt came up with the idea, and Russell did the rigorous math. And what they came up with is that everything about a star is determined by its initial mass and composition. What is it made of? And we know most modern population stars are about 74% hydrogen, about 24% helium, and about 2% lithium and other things. If you take the composition and how much is it? How much mass do you have? If you plug these two things in, you essentially know everything about the star for its whole lifetime. You know how big it will be, how hot it will be, what color it will be, how fast it will fuse hydrogen, what kind of fusion is present. Do you have hydrogen fusion, helium fusion? Is it a carbon-burning star? How long will it live? How will it die? Will it go in a nova or a supernova? Will it form a neutron star, a white dwarf, a black hole? All these things are determined by initial mass and composition. Allow me to give you Barth's corollary to the Russell-Vogt, or the Vogt-Russell theorem. It's a lot of times listed as Russell-Vogt because Russell is more famous, but in fact, Vogt came first by about 10 years. I think if you take planets, initial composition and mass, you pretty much know everything about the planet, how big it will be, whether or not it can hold an atmosphere, whether it will be an ice giant, a gas giant, a terrestrial planet, or a barren, rocky, water and atmosphere-less world like Mercury. And so, yes, if you have an object floating in free space that's between a half a Jupiter and 5 to 7 Jupiters, yes, you've got a planet. It's not around a star, but that doesn't change what it is. And that's how we know. So Professor Makarian, to go back, says, gee, clouds like the Orion Nebula are not supposed to be able to make planets directly. They're only supposed to be able to make stars. And it's in new young star systems where the dusty disk forms around planets, and that's where you get compression and accretion, and planets and objects collide together and build up and form planetoids and then true planets. And he's like, gee, it's not supposed to be there. We're not supposed to be able to form Jovian-sized objects directly. And his quote was, we wanted to see if we could break physics. And I think we have, which is good. So when we talk about stars forming, how does it really happen? And interestingly enough, although stars fuse hydrogen into helium, and this fusion process powers a star, it generates all of the star's energy and heat and light and gamma radiation, and all these things are all powered by hydrogen fusion. But in fact, if you had a pure cloud of a hydrogen helium mixture, 75-25, primordial cloud of gas, say just after the Big Bang, these large clouds of pure gas have an awful time forming stars. These population 3 stars, the very earliest population of stars in our galaxy, these stars were as much as 1,000 solar masses. The biggest star we know of today is about 100 solar masses.
Dr.
And sir.
We've got another question here.
All right.
And that's, John Ray says, will these findings affect the long-accepted Hertzsprung-Russell diagram regarding the evolution of stars, or is it unaffected due to these objects being failed stars?
Good question, John. When you talk about failed stars, what most astronomers are referring to is brown dwarfs. And these are objects between roughly 10 to 80 Jupiters in mass. The threshold for where does a star form, there's a lot of argument about that. This is one of those bleeding edge questions where you can start a fist fight at an astronomy conference by asking this question. Astronomers argue about this, and there's different models, but we know that somewhere around 80 Jupiters, the compression is great enough to get to that critical fusion temperature of 10 million degrees at the core, and then fusion is initiated. Now, can you get a star to burn smaller than that 80 Jupiter threshold? Yes, we think so, but the mechanisms are not clear. We do know that what we call failed dwarfs are brown dwarfs, failed stars. They're so much bigger than Jovian planets that they don't really fit in the same class. And unlike a Jovian, they emit their own light. However, they don't emit visible light. They were once called infrared stars. They were predicted in theory, but no one had seen them. We've seen some now. They're extraordinarily difficult to detect. They are off by themselves. They do not glow in visible or high energy frequencies at all. And they're only shining in infrared. And it's a really tremendously difficult challenge to detect things with infrared inside the Earth's atmosphere, really at the bottom of our ocean of air. Hence the James Webb Space Telescope. We're hoping we'll find more brown dwarfs. And when we find more brown dwarf stars, we'll be able to get a better idea of their mass limits and how they work. But in fact, they do not have a fusion core. They are objects which have been compacted. Say you've reached a temperature at the core of 5 to 7 million kelvins. Not hot enough for fusion, but certainly hot enough to glow in the infrared. And these stars would have, or failed stars, brown dwarfs, would have a surface temperature of some hundreds of degrees centigrade compared to our sun at about 6,000 Kelvin. These would have much lower temperatures. And when we talk about forming these stars, as we said, if you had this primordial cloud of just hydrogen and helium, you have to have an enormous mass before you get a star. And these population 3 stars would have been very short-lived, perhaps a few thousands of years, compared to the millions or billions or trillions of years we expect of stars that exist now. Why? They didn't have any dust. Well, what's the big deal? The difference between gas and dust, of course, is that dust is a solid particle. So you may be talking about a few grains of carbon sticking together. There may be grains of silicates or other materials that can survive in those temperatures. The thing is that these dust grains have a tremendous amount of surface area. Think of something that looks like a sponge, right? A clump of a few 100,000 atoms. It looks like a sponge. It has a tremendous amount of surface area. Every bit of that surface area can radiate heat. The most efficient radiators of heat ever are these primordial dust grains because they have such a huge surface area. What's their function in making stars? Well, again, if you've maybe studied a little basic chemistry, you may know something called the gas laws. And maybe I'm giving you flashbacks and PTSD right now from old chemistry classes. Fundamentally, gas laws say if you heat a gas up, it expands. If you compact a quantity of gas, it warms up. So you have this function between heat and compression. Well, if you have pure gas and the cloud starts to compress by gravitation, it warms up and this forces it to expand back. And so you get this equilibrium where the core is not hot enough for fusion. What does dust do? It radiates heat away from the outer layers. Keep in mind, if you're talking a sun-like star, a yellow dwarf, the core is a long, long way, hundreds of thousands of kilometers away from the outer photospheric surface. So if you have a star that contains a certain percentage of dust, astrophysicists call this metallicity. Astrophysicists have a little bit different view of chemistry in the periodic table than the rest of us do. Basically, everything above helium is a metal. And if you get these high metallicity stars, what happens is you get more dust grains. The surface can radiate heat away, which keeps the internal layers from getting too hot and expanding too much. And so dust forms this lovely natural radiator that allows the core to be further compressed and heated. And with a metal-bearing star, a dusty star, you can't get a star more than 100 to 120 solar masses because it's already started reacting, it's already started its fusion cycle, and as soon as that happens, yeah, guess what? Fusion is a tremendously energetic reaction. Once fusion starts, the outer layers of gas and material are blown away from the star's surface, and a lot of this material coalesces into this dusty disk, this ring, not unlike the rings of Saturn that circles the star around its equator. And the physics of this is very clear. This dusty sphere will tend to collapse and flatten. That not only increases the pressure, but brings particles close together so they can collide and stick and aggregate together, forming larger and larger particles. This is how we make planets. But these stars, modern stars, depend on dust. Where does the dust come from? Early stars would have gone supernova very, very quickly. And we know that supernovae are element factories. A normal star can fuse elements up to iron. And once you reach iron, there's no more fusing into bigger elements. And iron, of course, element number 26. And we know, oh, there's 115 or so elements in the periodic table. Well, why can't we get bigger than iron atoms in a regular star? It turns out as you fuse larger and larger atoms to make bigger and bigger elements, you get less energy out. And finally, when you reach iron, you can fuse elements to make iron, but you can't fuse iron and get any energy out. If you're going to make elements bigger than iron, you have to add energy in. It's no longer an energy releasing process, it's an energy consuming process. And so this is why we need big explosions such as supernovae or really big collisions such as neutron stars to create the heat and pressure needed and have the energy budget. So much energy in a supernova explosion that there's plenty to raise the temperature to hundreds of millions degrees Kelvin. And this gives us the ability to, if you will, forge these larger elements. So dust is really important. Next time you're sweeping up and dusting your house, remember two things. One, that dust helps create stars. And two, the dust you sweep up in your house and off of your tabletop surface, some of that dust comes from burning meteorites in the atmosphere, and that dust trickles down. So some of that dust is extraterrestrial in origin. So let's go back to Professor Makarian and his comment about breaking physics. What was he really talking about? What are we doing when we break physics? Well, friends, a good scientific theory, if it's really a scientific theory and not just somebody's, what we call a WAG, a wild guess. What the A stands for, I'll let you figure out. But a WAG is just somebody's crazy idea. But a true scientific theory is a tremendous accomplishment because it has to do two things. A true scientific theory has to explain everything we know about a current topic. You think about that. Oh, I have a new theory. It's not what everybody has always thought. I don't care what you're talking about. You know, pond life, evolution, stellar formation, the Big Bang, doesn't matter. Oh, I've got a new theory. First of all, you have to explain everything that everyone knew before. The second thing we have to do, of course, is a good theory, a scientific theory will tell us, you need to look in this place over here because my theory predicts you'll find new things. You'll find new processes. This is why Einstein's relativity was such a fabulous advance in scientific theory. It not only explained everything we knew about gravitation, but it explained some things that had defied explanation for years, such as Mercury's crazy precession of its orbit. And it explains all sorts of things, black holes, different stuff like that. Well, but it also says, oh, if you look here, you should see new things. Einstein, of course, among other things, predicted that if you are moving very fast relative to me, you're flying past me in a spaceship, your clocks run slower than mine do. And so we look at this new phenomena, and sometimes they seem relatively trivial. Oh, I predict there should be a new species of ant existing in Arctic places, and we need to go look for that. Excuse me. But sometimes new phenomena can be truly revolutionary. And my favorite one of those, relatively modern, Professor Vera Rubin, and her discovery that galaxies don't spin the way that planetary systems do. Planetary systems, all the planets move in what's called Keplerian orbits. The farther out you are, the slower you move. But galaxies, excuse me, everything orbits at the same speed no matter how far out you are. And so, wow, this has led us on a quest for dark matter or new gravity. We're not sure which. So finding these Jovian mass rogue planets in Orion in the M42 Nebula was very unexpected. And when we find the unexpected, we have to do one of two things. Either we have to adjust an existing theory to accommodate the new discovery, or it may be that crack through which we realize, oh, we need a whole new theory. People tried for about 75 years to explain Mercury's precession, and they tried to explain it with standard Newtonian gravity, and the result of that was a wild goose chase looking for a planet that was christened Vulcan. Has to be really close to the sun, and it could be just bumping, nudging Mercury, and so creating this very small effect. Einstein rejected that and said, no. We need a new theory of gravity. And we all know how that story worked out. Einstein won. I won't say Newton zero. That would be disrespectful. Einstein is famous because he's the first man in 350 years to make any tiny correction in Newton's theory of gravitation. So,
Hey, that's my great grandfather.
outstanding. Our producer, Paul Newton, and it's not
He literally
just,
is. We did the genealogy on it.
I believe you.
Actually,
But
he's my great, and etc. uncle, because his brother was actually my grandfather.
There you go. And it's not our long friendship that makes me respect your ancestor. He earned that on his own. Anyway, but the other thing is these jumbos, they found some of these Jupiter mass objects in close binary relationships. And that was really unexpected. Oh, it makes Jovian mass objects? Okay. Maybe we need to revise our idea about how stars form in dense nebulae. Maybe they can make, but why would these things be in binary orbits? And they found dozens of them. They found hundreds of Jovian mass objects. Some dozens of them were in close binary relationships. It's kind of funny. And part of the question came up, could the jumbos actually be protostars? And this really seems unlikely. All the protostars we know, remember a protostar is that stage when the nebula is contracting, the core is getting really hot, and it's hot enough to glow in the infrared. So this is brown dwarf type stage, but for a successful star, the brown dwarf shining in infrared is only a passing phase because the core continues to compact. It's massive enough to crush the core, to reach the temperature, fusion starts, and you get a true star. Kind of like Pinocchio saying, I'm a real boy now. Although Pinocchio did not have a fusion core, and Geppetto was very happy about that. So, sorry, bad joke. Our sun, our yellow dwarf star, is about 1,000 Jovian masses. The smallest known red dwarf stars are about 0.3, or about 30% of the mass of our sun. And we think that stars as small as 0.1 or 10% of a solar mass are considered possible. They're really hard to detect, and in nature, of course, when something is smaller, we tend to have more of them. There are far more ants than people, and there are far more bacteria than ants. If you go to the moon and count craters, there are far more teeny tiny craters than there are great big craters. And this hierarchy of numbers based on size is something that's found throughout nature. Smaller objects than red dwarf stars. These are between the 15 and 90 Jovian masses. Those are about 0.015 to 0.09 solar masses, or they get up to almost a tenth of a solar mass. There's your brown dwarf region right there, friends. There's your brown dwarf region. They do glow in the infrared. They're not true stars. They have no fusion core. They don't produce anything new. They're going to eventually cool off and compress into a white dwarf that will take a long time. It's not unlikely that M42, the Orion Nebula, is producing red dwarf stars. What we know now is that red dwarfs are the most common star type in our galaxy, and probably in all galaxies, just that hierarchy of there's more small things than big ones. So when we look at this, we don't really understand how red dwarfs form. Why does a red dwarf stop at that limit so far, a third, a tenth to a third of a solar mass? Why do they stop? Why do they become stars? How come they don't collect more material? And that's a mystery. So is there a new mechanism for forming both red dwarfs and brown dwarfs and these Jovian mass planets? Because it's always been thought that small objects like Jupiter and Saturn and Neptune and Uranus, which are our gas and ice giant planets, that these small objects only form in the dusty disk surrounding newly formed stars. We've never seen nor had a theory account for how something like a dusty nebula like Orion could be cranking out Jovian-sized objects, much less Jovian objects in binary pairs. Now, the binary part isn't strange. Surveys indicate, and this may blow your socks off, it surprised me when I first learned of it. About 85% of stars that we know of that we can survey directly exist in a binary or higher order relationship. You think about that. You look out in the night sky, 85% of the stars we can see have at least one companion. Some have more. And what's going on here? Are these Jovian mass objects simply clumping together and then gravitationally linking up and spiraling off into empty space? We don't know. These rogue planets that we've observed through stellar eclipses, we don't get a chance to see them well enough to know if they're single or binary. We don't have any, we observe them indirectly. We see a star dip. It happens once. It doesn't happen again. It had to be something passing through that star system close enough that it would eclipse the star significantly. And if that happens, we should be seeing it eclipsed regularly. That doesn't happen. We figure, oh, it was a rogue planet. There's a lot of science and math there. And as far as multiple star systems, the highest and most complex multiple that we know of, certainly that I know of, and somebody out there may top me on this, is the star Pollux, which is in Gemini, which we'll be looking at this winter. Always one of my favorites. Pollux contains 6 stars. I learned that. This is just nuts. It contains what is a visual binary pair, but that binary pair each contains 2. And so you have 2 eclipsing binary pairs. They're so close and so tight that we cannot resolve them directly, but we see by the light curve, we know that one is eclipsing the other. And it's when you have 2 stars in a eclipsing relationship in tight orbits, the light curve is very distinctive so that it's like a fingerprint, you know it's there. So we have these 2 binary pairs circling around each other, and then we have a third binary pair that's so far away. It's in an orbit of about 20 to 25,000 years compared to these eclipsing binary pairs at the heart of the Pollux system, which eclipse each other and orbit each other in just a few days. So we looked at this system, and it certainly seems that Professor Makarian is correct. We've kind of broken the old theory. We've broken physics, or astrophysics if you prefer, because all the science we know now says, no, nebulas don't form brown dwarfs, and they certainly don't form Jovians. Of course, how do brown dwarfs and Jovians form? We always thought these were formed in a star system around a central star. Brown dwarfs, there's not a real good theory for how they form. Why don't they just keep growing? If you think about an environment like the Orion Nebula, there's a huge amount of gas and dust there. Why do they stop accreting material? If you think about the way we believe that a Jovian planet forms, the crucial thing for Jupiter and Saturn is that, like our sun, they are 95% hydrogen and helium. Well, how did they get this? Earth can't hold either hydrogen or helium at all. If you have a toy balloon filled with helium and you let it go, it rises up into the atmosphere, the pressure gets lower, the balloon expands, eventually the balloon will pop, and the string and the latex envelope will fall to Earth. The helium inside the balloon is lost to us forever. Helium is a non-renewable resource. If you, do a party trick where you inhale helium and talk all funny, don't do that. It's not a safe activity. But if, like I said, you release a helium balloon and it pops, that helium is never coming back. Unlike the balloon's envelope and the string, which fall back to Earth, the helium will go up to the top of our atmosphere. It will get excited by solar radiation. It will reach escape velocity, and it will escape into space. It never comes back. Well, why don't Earth, Mars, or Venus have hydrogen or helium in their atmosphere? It's simple. They're not big enough worlds. They don't have enough gravity to hold these very light gases in their atmospheres. When you get a planetary core that reaches about 3 to 5 Earth masses, and again, there's arguments about this, but it's somewhere certainly by 5 Earth masses, you've got a core which is large enough that it can now hold hydrogen and helium. Consider a planet swirling through a gassy, dusty ring full of hydrogen and helium. If it's an Earth-sized planet, it's like a fish swimming in the ocean. It can't drink all the water it swims in, it just swims through it. But if you get as big as the core of Jupiter or Saturn, somewhere between 3 and 5 Earth masses, all of a sudden you're not swimming through the ocean, you're scooping the water up as you go. And once they reach this critical stage, we believe that Jovian planets' atmospheres accrete very, very quickly, that you might go from that threshold level of a rocky super Earth to a Jovian planet with an atmosphere that outweighs your planet core by hundreds or even thousands of times in only 1,000 years or so. Once you start scooping up all the water in the ocean rather than just swimming through it, yeah, you collect a lot of material very, very quickly. And of course, the faster they grow, the more gravity they have, the more hydrogen and helium they accrete from the local environment until finally that material is used up, or the star entering an energetic phase blows that gas out into the interstellar medium again. So why, in fact, do brown dwarfs stop? If they're in a nebula like Orion, why don't they continue to accrete material and form protostars and then real stars? Will these jumbos, in fact, continue to accrete material and eventually collect enough mass that they become brown dwarfs, protostars, and real stars? Will they, like Pinocchio, become a real boy? Will they initiate fusion at their core when they collect enough material? Nobody's sure right now. And Professor McCorian is right. We've broken our theory, and I'm very excited to see what new science emerges. I know all the very clever mathematically oriented astrophysicists are going to be cranking up their models and trying to see if they can find a model that works for producing these objects. So we're looking forward to exciting new science from this discovery from James Webb Space Telescope. If you'd like more information, very much encourage you to go to the Explore Alliance live webpage and look up How Do You Know, episode 84. And you can download our show notes, which has lots of links for you. One of the most exciting ones is called ESA Sky, the European Space Agency's Sky program, where you can tour the whole sky, zoom in, and they're basically mapping that with Webb and other data. Really, really exciting stuff. So there we go. We're also going to let you know this is episode 84. We'll be coming up sometime in the spring on episode 100 of the How Do You Know program. If you have something, we'll think of something special for the 100th episode. If you've got an idea of something you'd like to see, put something in the comments or drop me a line, and you can reach me at astronomyforeducators@gmail.com. You can also reach me at drbee@explorescientific.com. So drop a note at either one of those email addresses if you have a special idea for the 100th edition of How Do You Know? And with that, we'll bid you all a good afternoon, and we'll see you again next week.